So hello everybody, my name is Alexandros. I'm a postdoc with Vikram, and my other collaborators are Michael Han from Autodesk and Richard Latham. Today I'll talk to you about ASAP, annotations for safe parallelism in Clang. So motivation, this is probably very well known to most of you. Parallel debugging is hard. A lot of bugs depend on interleavings, such as data races, atomicity violations, etc. So you'd like to have some sort of tools to help you do that. They're hard to reproduce. So there's sort of two types of tools right now: dynamic tools, such as race detectors, and each type of tools has their own sets of problems. So dynamic tools typically don't give you any guarantees. They might give you some sort of guarantees about the code they run through, but by no means about the entire code that the application is made of. A lot of them have very significant overheads, preventing them from being deployed at the user. So they're usually just for the testing phase. And sometimes, depending on them, they might also have a lot of false positives. Static analysis has their own problems. The nice thing is they catch bugs. They have the potential to catch bugs early before even testing. They are plagued by false positives a lot of the time. Sometimes they require interprocedural analysis, which is expensive and takes a lot of time, and sometimes they have a limited scope. Our approach is a static analysis approach. It gives strong guarantees, so race freedom and strong atomicity. There are some things that we're assuming, but I'll come to those a little bit later. The checking is modular, so the good thing about that is all the annotations can be checked one function at a time. This allows for a much better performance. We don't have interprocedural analysis for checking them. It's an annotation-based approach, so these annotations allow a rich expressiveness of of complicated parallelism patterns. They are checked, so the annotations are checked. We don't trust that the user will write the correct annotations, and sometimes the code changes. We don't want them to drift apart, so annotations are checked, and I'll talk about how this is done. And as with other systems, you can use annotations to silence or blacklist things, to silence false positives. So one of the big drawbacks of this approach is the annotation burden can be pretty heavy. So we're working on full inference. So this is in progress. I'll talk a little bit about it towards the end. A little history of the project. This is rooted in the Deterministic Parallel Java, which started by supporting deterministic parallel fork join algorithms, then also implemented some partial annotation inference, added some non-determinism a couple of years later, as well as support for frameworks. And recently we had an extended programming model that combined static and dynamic approaches for tasks with effects in Java that allows more complicated types of parallelism than just fork join. For the ASAP project, which is what I'm talking about today, it's a collaboration that started around 2010 with a design phase. It's a collaboration with Autodesk, and the implementation is now in Clang. So with Autodesk, we've been talking with Michael Han and Richard Latham for over the past year and a half, every week, getting active feedback about what it is in their source that they could use in terms of static checking of parallelism. So some of the things we've been covering is like, what are their common parallelism patterns that they'd like supported. And one of the things, for example, is when you take a large legacy code that was designed a long time ago and you want to parallelize it, globals tend to be a big issue. So finding globals that are accessed either directly or through aliases is an important concern for that process. More specifically, we're working with one of their libraries, the ASM library, that has, it's a pretty big code base that's between 3 and 4 million lines of code used internally at Autodesk. They use structured parallelism, so things like parallel loops and scoped locks. But external parallelism, the client is free to use non-structured parallelism, such as pthreads, for example. And one of the important issues is, there's this library API that has some specs that the clients are allowed to, for example, call a function in parallel with another function as long as they don't call it on the same object or things like that. So there's some handwritten rules about how the API is allowed to be used. And we would like to be able to use and formalize those and both check that the library itself is safe with regards to those specifications, and also in some cases when we can check that the client honors this API. So here's the outline of the rest of the talk. First, I'll talk to you about what these annotations are, what they look like, and what they do. Then I'll talk a little bit about how this is implemented inside of Clang, and then I'll just talk about what's to come. This is still a prototype, and we have a lot of plans on what to add to it to make it useful in practice. So here's for the first part. So our annotations are like there's regions and effects annotations. A region is essentially a group of memory locations. Could be one, could be multiple. These regions are disjoint from each other, but there's a hierarchy that I'll talk about that allows to express different sharing patterns. And also these regions allow controlled aliasing. So for example, you may have a pointer that's in region R1 and is allowed to point to any memory location in some region R2. So we can use controlled aliasing as opposed to uncontrolled, where a pointer can theoretically point to any memory location, at least, if you ignore type safety at least. So effect summaries per function, we have an effect summary. These allow the checking to be modular. So the effect summary describes essentially in terms of regions, what does this method do, which regions it reads, writes, whether it reads or writes them atomically or holding some lock. This is still future work. For now, we're only doing reads and writes. The effect summaries make the checking modular. So essentially, when you check a single function, you trust that all the other effect summaries are correct, but then you check that this effect summary is like the statements of the function, their effects are covered by the effect summary. And so these are checked and not trusted. And then once you have this in place, parallel safety boils down to non-interference of effects of tasks running in parallel. So if you know what things are running in parallel, you can reason about whether the parallelism is safe or not. So here's an example with a very simple class that we're going to annotate. It's a point that has two fields, the coordinates, has a couple of setter functions, very simple ones, and one that sets the two fields in parallel. Here I'm sort of abusing a little bit the lambda notation to make it it's a little shorthand for the slides. So in this code, we'll want to be able to show that calling these two things in parallel is safe. So we want to be able to distinguish between the regions of these two fields. So we can do that by declaring two region names that are Rx and Ry, and then X is in that region Rx, Y is in region Ry. Then we fill in the effect summaries, pretty simple. And then the non-interference down here is basically done by checking that the effect of the left-hand task, writes Rx, is disjoint from writes Ry. Okay, this is pretty simple stuff. Note, however, that right now these fields are in this region Rx. So if you had another object of the same type, the X field would also be in Rx. So this is not sufficient. We want some more. Here's, by the way, what these annotations look like. Actually, we're using the C++ 11 attributes to encode these annotations. And I'll have a short demo later, but this is sort of what they look like, just the ASAP prefix and then region declarations, arguments, and write effects. So now we're going to do an example with object distinction where we'll be able to set the coordinates of two different points in parallel. So, okay. So in this case, we're adding a region parameter to the class that allows us to distinguish between instances, different instances of the same type of object. And now the coordinates are in that region P. The set function, which is sequential now, writes to that region P. And then we can write a function foo that takes 2 points, one in our region R1, one in region R2, and sets them in parallel, and that's safe. We can also make this parametric, so they don't have to be fixed region names. We can have points in different regions and have a constraint saying that these 2 points have to be in different regions. And now we're going to combine those two things we talked about, field distinction and object distinction. So this is the sort of the way you would write this class to allow the maximum parallelism. Pretty simple example, but it's just for illustrating. So we still have this region P. We have two region names X and Y, and then field X, coordinate X is in region X under P, and the Y is in region Y under P. So these two regions are disjoint, P colon X and P colon Y. And so that allows us to reason that these two tasks of setting the X and Y coordinate are non-interfering because they write to P colon X and P colon Y. And we still maintain the object distinction by having the parameter there for when we check the parallel invoke over 2 points. We can also summarize these effects a little more concisely by using this wildcard star here that just says that this function writes to all of the regions that start with R1. And we'll see a little bit more about this right now. This is just to show the expressiveness of these region, we call them region path lists, RPLs. So basically these things that have names or parameters separated by columns. So we are assuming that there's a root name, a region called root that's at the beginning of every region, RPL, region path list, and then when we write T1, we actually mean root colon T1, similarly T2, root colon T2, and then we can reason that these are disjoint. When we write this with a wildcard, we can include all the regions that start with T1. And note that these boxes that are different names, they're all disjoint regions. So this allows us to group them together and talk about them collectively. And so T2 colon star is that, and again we can reason that these are disjoint sets of regions. Now this one is the region D that's under T1. This is the under, we call this the under relation. They're still disjoint, so these T1 and T1 colon D are disjoint. And then the inclusion properties that T1 colon D is included in T1 colon star. And then finally, the distinction from the right, which allows to distinguishing between accesses to fields in more complex data structures. So this RPL right here means all the regions that have a T1 at the beginning and then end with a D. So this one, and there might be other ones down there. Similarly, that RPL is for the link ones. And so again, we can reason that these sets of regions are disjoint. So with all that in mind, we can do a nice little recursive example. We have a list node with some data and the pointer to the next node, and a method that sets all of the data fields of a list to some value x. And it does that by setting the value of that, this field, of data field to x, and then if in parallel, if there's a next, if the pointer to next is not null, it will call itself recursively on the rest of the list. So this is, I don't think anyone would write this code in parallel specifically, but it's for illustration purposes and how this works. So we are adding this region parameter as before. We're declaring 3 region names, and data is in p:(d). Now the pointer has 2 regions. So the first one is where the pointer lives here, p:(link). The pointer itself is a field of the node, and then this one is the argument of the list node. So since it's parametric, we have to give it an argument. And so this allows us to distinguish between consecutive list elements and have them in different regions. So what this function does essentially is it sets, as we said, it sets all the data fields of the list. So this is writes p*d. So starting from the point that we're at and all the next ones, we're modifying d. And to get there, we're reading all the links. So it reads p:(link), which are all these next pointers. And so far, we haven't seen any of this p:(n). And this is appearing here in the non-interference, where if we look at the effects of the 2 tasks, the first one is very simple. It writes p:(d). The second one is a little bit trickier. It reads this p:(link), and then it invokes this function which has this effect summary, but with the parameter p substituted with p:(n). So essentially the effects of this call are reads p:(n) star link by replacing p by p:(n) over here, and the writes here similarly. And then we can argue, we can prove that this is safe by looking at this and seeing that indeed writes p:(d) does not interfere with any of these effects of the other task. With that said,
so
yeah.
when you have a circular list, sir, can we wait for questions until after, please?
Okay, let me get to the demo. All right, let's see. So we have this point class again. It's a little different now. We have the 2 fields x and y. Where's the... Okay, 2 fields x and y. And we also have a static variable of the same type point. That's the origin, where, let's say, all these points are relative to some origin. And a couple of constructors, but let's focus on the functions. There's 3 functions set, which we saw before. Move halfway to origin, which essentially moves the point close to its origin, so it reads the point. And finally, one that just moves the origin by some vector. Also, one thing to notice is here the point doesn't have a region argument. This is just, we could have put in one, but by default, globals and statics are in this region global. If we want something more specific, we can manually add it. So the parallelism in this example is in TBB, and since we don't have yet support for lambdas, although that's very high on our list, we have used the functor approach. So the functors just do the same things as those functions that we just saw. And let's just have a function foo and try and play a little bit with it. So don't worry about the effects of foo. It's just there to cover all of the things we're going to be doing. So basically, we're starting with 2 points, P1 and P2. And just for illustration purposes, we're putting all these points in regions under points. So this one is in points colon P1, the next one is in points colon P2. And then setting them sequentially is not causing any problems. There's no question of parallelism here yet. But if we do them using functors, we can create those functors and invoke them in parallel. And as I showed before, this would be safe. Let me make this font a little bigger. Okay. So no output means there's no issues, okay? So now let's do something a little more interesting. It returns without crashing, yes, it's a big progress. So here let's do something more interesting. So now we have a pointer that can point to any object of type point that's under point. So it could point to any of these two points that we have. So we can start by making it point to P1 and then create a functor for it, and then try to also first just to see that this aliasing is still okay, no problems, fine. When we're trying to update both P1 both through the P1 functor and the P star functor, then we'll see that finally we get some output. And here we see, so this effect, reads effect on read-only, is just an artifact of the current implementation that we're going to fix, so we can ignore this for now. But it says that these effects interfere, so writes effect on points colon P1, point 1 colon star interferes with this write effects on points colon star, etc. So this is not safe code to run in parallel. So for the next part here, just to show that we can change the aliasing of the pointer to point to P2, that's fine. There's no problem with that. Now again, a little bit something more interesting. We're creating these two functors that move the points towards the origin, P1 and P2, and we're calling them in parallel. Let me save that. And now we'd expect that this be fine, but it's not fine because we made a mistake and we called the functor to move the same object, P1, towards the origin. So this is modifying the same point in parallel. So there's a race there. So if we fix that to do what we intended to, then again, it's safe. And finally, here we're creating another a functor to just modify the position of the origin by some vector. And if we try to modify the origin and also modify a point by moving it close to the origin, again, we'll see that we're able to catch this sort of error. Here the conflict is because we have a writes effect on global in one task and a reads effect on global in the other task. And but if we're just moving the origin and setting a point, even if it's through the set star functor, which is not clear which point it's modifying, then we can actually do that safely. So it does cover a number of, excuse me, let me get back here, different patterns. So to get to the how it's implemented, so sort of its architecture, it has 4 sort of sets of passes. The first one does some semantic checks on the annotations. It collects names. It makes sure they're well formed, that we're not passing an argument that wasn't a declared region name, that the arguments there's a correct number of arguments for each type, all sorts of things like that. One other thing is, for example, when you have multiple declarations, you want the canonical declaration to have, for example, the effect summary that covers the effect summaries of the other declarations. So trying to make, to be sound, of course. And then we also have a pass that we detect the parallelism that, for example, TBB that we're targeting right now, detecting their parallel API. All of that stuff is using the recursive AST visitor. And the next 3 passes are essentially using a statement visitor. The type checker makes sure that you're not, for example, aliasing, so pointing to a region that the pointer is not allowed to point to. If you have a pointer to R1 and you try to take the address of something that's in R2, then the type checker will complain. Effect checker checks that the effect summaries are conservative, that they cover all the effects. And finally, the non-interference checker does the checking that the effects are non-interfering. So this is right now implemented in our private clone of the Clang repository. It's under the static analyzer checkers. We don't currently rely on any of the analysis, so we could actually rewrite this as a plugin or using the tooling infrastructure. We have a custom symbol table, which is taking a lot of the implementation overhead, where we're extending types to have these extended semantics with regions and effects. And it's starting to grow to be a relatively large checker with so far 6,000 lines of code, but quite a few more to come. So Michael Han, who's here, has helped a lot with the project by making a lot of contributions in terms of patches, especially for the C++11 attribute system. These are listed some of them. There's a few more. And also one bug reported and fixed for the recursive AST visitor. So scope and limitations. So first of all, non-interference right now, checking non-interference is right now limited to structured parallelism and for now fork join, although I think we could probably target a few more other cases where we can reason statically about what's running in parallel. We're making a couple of assumptions about the program, that it's type safe and memory safe. Please use tools to make sure that that's the case anyways. So right now in C++11, attributes are not allowed everywhere we would like them to be allowed. So for example, when you have a function call, you can't put an attribute on that. We have some ways around that, but it'd be nice to maybe influence the next standard. And also includes, actually, if one wanted to break our soundness, they could use some include tricks to confuse and to make it impossible for us to check that the read declarations are consistent with each other. Current implementation limitations, there's a lot of them. This is still a prototype. Most notably, we don't analyze standard libraries yet. If you have type unsafe things right now, we're not even issuing a warning. One of the reasons is I haven't found how to add flags to checkers other than having separate checkers. Function pointers is a big one, but we'll get to that. Lambdas is a big one that is very high on our list, and so on. There's a short wish list. So I'm having trouble with Clang. If anyone knows how to integrate custom checkers with the driver, like passing flags or selecting options, please find me and let me know. This one is almost for fun. Pluggable type system support, maybe someday. Maybe I should do that at some point. And C++ has a few limitations. I kind of touched on this earlier. Finally, a couple of things for future work that we want to add. Right now, we only have support for parallel invoke. We obviously want to support all the APIs of TBB, but also other libraries like Microsoft Concurrent that has very similar, if not identical in some cases, API. And perhaps we can actually come up with some sort of annotation to annotate those APIs instead of hard coding knowledge about them. As I mentioned earlier, libraries have interesting problems. So for example, we would like to think of annotations such as, like, say that it is safe to call function f when the first argument is in region R1 and call it in parallel with another clone of f when an argument in some other region R2, if and only if these regions are disjoint. Also, the issue that I mentioned about taking legacy C code and moving it forward and dealing with globals. This one, especially without requiring any annotation. Index parameterized arrays, this is a big one. This is in DPJ already, so we know how to do it. It's a matter of implementing it. Let me silence this. So a lot of times we have arrays of references, and we want to be able to reason about the fact that all these pointers point to separate objects, and there's no case that two of these pointers point to the same one, because we want to do a parallel update on such a data structure. So that we can add index annotations to types, to base types of arrays that have an index that's also coincides with the index of the array. So then we can reason that this case will never be possible. So essentially, it gets in the extended type of the object pointed to. Annotation inference, as I mentioned, is a very big concern because these annotations could get a little bit heavyweight. So as I mentioned already, one of the effect summaries annotations are already being, we know how to infer them. There was a paper in 2009 about this. And this is solving the effect summary coverage constraints only, but we want to extend this to full inference, and this is a lot trickier because we're solving three types of constraints at the same time, both the non-interference constraints, the effect summary coverage, and the subtypes, so being able to assign a pointer to some address or something, and so we have to solve all these three at the same time. Just a quick example with that list node that we looked at earlier. Here we are assuming that we know it's taking one parameter. Then the inference would do something like plug in variables where actual annotations are needed. So pi, pi1, pi2, and e for the effect summary. And then compute the effects as a function of these variables. And then produce constraints as functions of these variables, the effect coverage effect and the non-interference effect. And these get tricky fast because, for example, in this one you see that the effect summaries contains itself recursively. So it's a very interesting problem for me. Finally, locks. I haven't talked about that at all. Our plan is to start with scoped locks and take advantage of the thread safety annotations. A lot of the work can be reused. Last time I checked, I don't know if this has changed. There was some limitations about aliasing, accessing locks through aliases. We'd have to think about how to overcome this as well. And then also we'd want to oh, by the way, I'm not suggesting that thread safety annotations only work for scoped locks, but it's just where we want to start with, and then extend to other types of locking. So for concluding, we're hoping to provide a checker that provides, we know it can provide strong safety guarantees. We have a functional basic prototype, and we want to work on the annotation inference to make it usable by normal programmers who don't have PhDs and want to do postdocs in static analysis. Also, we want to work on library API contracts so as to be able to modularize a little bit the checking and the inference parts of things, and a lot more. So thank you very much for your attention. And
so just real fast, I want to make sure everyone uses the microphone to ask questions, and you've got about 5 minutes for questions.
thank you.
So I'm going to ask you an academically unfortunate question. How is your effects analysis different from the Greenhouse-Boyland OO effects analysis from 2003?
Can you repeat the?
Aaron Greenhouse and John Boyland at CMU did a precise OO effects analysis for Java in the early 2000s, which is well published. And my notes, as you were walking along, basically say, as far as I can see, you've got Greenhouse-Boylan analysis, but with more annotations. So what did I miss? How is it different?
Can I take it?
Sure, yeah. You probably take the microphone.
What you do with it is different, but
Hold on, you should probably take the microphone.
Yeah.
Oh, I should
here, take the mic.
take So we've looked at Greenhouse-Boylan, and there's been a number of other effect systems like that. They're cited in our papers, and they're discussed in more detail, and you should look at that if you're interested. But the short answer is that Greenhouse-Boylan and a number of these other systems are much less expressive in terms of what kind of parallel idioms and data structures they can support.
That's what I wanted to hear.
Right. So the region path lists allow us to do hierarchical data structures and parallel updates on them, as well as things like index parameterized arrays, so where you have pointers, arrays of pointers to data, to objects. And those kinds of idioms are essential for real programs, and they're not really supported by any of those previous systems. So,
The indexed arrays was the only one I noticed that wasn't supported. But
okay.
anyway,
We can talk more
Cool.
about that. Yep.
I'll let other people have a chance to get more questions, though.
Okay, so if you go back to your example with the linked list, I just have a question on that one.
Yeah, for the circular linked list, right?
Yeah. So basically, my question is really, how do you annotate that if it's a circular list?
So right now, for a circular, is this it? Yeah. For a circular linked list, we don't have a way to annotate it and to be able to modify it in parallel. We can still annotate it and work on the whole list sequentially. That's fine. You can put all of them in a single region, right?
Okay.
And it's
Okay.
not parallel.
Right.
If you have a circular linked list, it wouldn't be parallel.
But on the other hand, depending on the condition, depending on your ending condition, right? So
Yeah,
if you can analyze your ending condition, then it can become parallel. But yeah, my question is really, do you have a past expression to express that?
Right now we don't. Actually, this is one of the things that I'm thinking about, and it might be possible. I don't have an answer yet to actually by having some sort of right here, maybe not on the declaration of the parameter, but have some parameter constraints that sort of give you some. It's similar to if you wanted to have a doubly linked list, you'd have to have a little bit more expressive power in how the parameters are constrained and initialized for those types of data structures. Right now we don't support it, but it's a good question, and I'm looking into that.
Thank you.
So this may be a sort of a trivial question. In your very first example, you show that it's safe to set the x and y in parallel, but it seems to make the assumption that the underlying architecture can actually do that. And the compiler, as an optimizer, it would be a stupid thing to do, could easily load a 64-bit value and change 32 bits or whatever the size was at a time, which wouldn't be parallel. So is there some...
You can't. That's undefined behavior if you do it that way.
I understand, but this would say it's safe to do that, and we don't know if the compiler was going to do that or not. And I've actually stumbled across a lot of bugs that essentially were a compiler optimization, did something that surprised everybody. And I was curious if there's a mechanism to sort of enforce good behavior or annotate it properly.
So enforce that the compiler has no bugs?
No, the compiler is free to make, I mean, if these had been bytes and your underlying architecture only did word access, wouldn't it be?
Not in C++.
Not in C++. You can only have that problem with bit fields.
Yeah, bit fields. Actually, I had this on the list of things that are not supported, and because of that reason, because right now we're not reasoning about what is going to be atomic when bit field. So right now we're assuming types are sort of atomic, or not atomic, but they're not in the same word, right? Any other questions? Now's your chance.
This is along the same lines of his question, though, but say you had a long, and you were going to be assigning to it on a 32-bit system. it seems that it seems like you're basically assuming that any access, a write or a read, is always going to be an atomic access of the variable, even if it might have to be loaded in two separate registers, for instance, in order to be modified?
Okay.
Or
So
am I just not understanding properly?
those two bytes, those two 32-bit quantities would be in the same region, though. So we would be able to reason that another task is if it's writing to the same region, so we
Okay.
would catch it. So that's not an
Okay.
issue.
Thank you.
Sure.
All right, everyone, that's it. Thank you very much. Next talk's in 5 minutes.